right, well, we are back at it and continuing with the Leetcode roadmap, and let's just go straight to the next problem. So we're on a roll today. Let's keep going. So 2 pointers, and next one is this one. So two integer sum number 2. Given an array of integers, numbers, that is sorted in non-decreasing order. So what does that mean? That means increasing order, but duplicates are there. Okay, return the indices, one indexed. Okay, so it starts at 1 of two numbers. Okay, index number 1, index number 2, such that they add up to a given target number. Okay, so index 1 is greater than index 2. Note that index 1 and index 2 cannot be equal, therefore you may not use the same element twice. Okay, alright, so your solution must use O of 1 additional space, okay? So let's see. We want to get to 3. Now, I selected this out of the 2 pointers section, but it would be nice for me to think about, like, how would I have identified that this is 2 pointers? And one of the things that 2 pointers has is that one of the questions that it's trying to solve is, okay, I have a list and I want to find the relationship between two of the numbers or two of the elements in the list. So that's how I'm targeting to see how they have a relationship. Now, the other thing that I can note is that this target is, there's a relationship between the target, or the sum, I should say, and the position of my 2 pointers. The reason for that is because as I move to the right, my sum is going to be bigger. Okay. So the first solution that immediately popped into my head was that I would have a pointer here and a pointer there, and I would move them over here, then move my, kind of like this, like ding, 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 kind of like this. But what is that? That's O of n squared time. I don't like it. Instead, I want to place my pointers one at the start, one at the beginning, and then move this way. And then how do I move them? Well, I know if my sum is too big, then I should move my end pointer over by 1. If my sum is too small, I should move my left pointer over by 1. And that way, if I move my left pointer over, it increases the sum. If I move my right pointer over, it decreases the sum. Okay, so let's do that. We have what? Now the other thing that I'm seeing though is it says index, they can't be equal, okay? But if there's duplicates in this array, then that might be an issue. Okay, there will always be exactly one valid solution, okay? Alright, well let's just code it up. So left is equal to 0, right is equal to length of numbers, and then -1. So while left is less than or equal to right, okay, should it be equal to? Can they, left and right, be the same thing? No, they cannot, so that's not equal to. So now I do value is equal to numbers indexed at left plus numbers indexed at right, okay? If val is equal to target, return, how does it want me to return it? Is it a list of the two? Okay, so list of left and, oh wait, no, we don't want the index, we want the value. So we want this. Okay. So if that's the case, we do that. And then elif value is greater than target. In this case, we want to move our right pointer over by 1. So right minus equals 1, else left plus equals 1. Okay? So then it says that there will always be a solution. So here we go. Now, do I need to check if the numbers are equal to each other? I don't. If I did, I would do something like this. So if is equal to each other, then I would need to run this again inside of here and then do a continue. But I'm thinking that this problem actually doesn't have duplicates because it says it here. It's like 1, 2, 3, 4. And I don't know, just we'll see about this. So it should always hit this return because it says that there's always a one valid solution. So let's see. Let's see if we did it right. Okay. Submit. Wrong answer. All right. Why? My output is this. It expected 1 and 3. Well, yeah, because 1 isn't even in there. Did it want the index? Hold on. Where does it say? Therefore, you may not use this. Return the indices. Okay, whatever. Indices. So we want. Okay, fine. Left, and then they say indices 1 indexed. Okay, +1. And right +1. There we go. Let's see if it's happy with that. All right, there we go. Cool, awesome. So we got that problem, and I guess we can look at the solution and think it's probably the same. So what are they doing? Binary search. Okay, hash map, 2 pointers. So they used this same thing that I did. Out of curiosity, I'm going to look at the hash map. Okay, so we have a map, okay, for I in range, and we have numbers. So we're going through however long numbers is. Okay. Target minus numbers of I. So this is how far off they are, right? It's how far off they are. And then I check if that number that I need is already in the map. If it is, okay, so what I think this one is doing is it's just going through the list, and it's seeing, okay, well, I know that I am, let's say, a 3, and my target is a 4. Okay. Well, what can I already know what would cause me to be able to have a valid pair, and that is a 1. Okay, because I'm a 3, I need a 1 to make a 4. So I check if 1 is in my map. If it is, then we return. And how does he know that? How does he know which one to return first? Because if there's a 1 already in there, I need to return the lower index first. Well, I guess because it's sorted and I'm going to see the smaller number first, that's why, okay, there we go, that makes sense now. And so this is index, so we return the index, and it's index plus 1, okay? If it's not in there, I can put that number, put the number that I'm currently at, right? Yeah. And then the value is going to be its index 1 indexed. Okay. Huh. Makes sense. Binary search is going to have left and right, okay? Here we find the middle. Okay. I plus 1, mid plus 1. Oh, I don't like this one because this one, the time complexity is much higher. No, okay, yeah. So it's a variation of the one that I was showing that I said is O of n squared time complexity. This one, so while I'm sliding this over, it still loops through each one of these, but this one just moves around faster and finds its target faster. But it's still, that would be O log of n, right? That's this one. And then binary search is log of n. So it's n log n time complexity, which, yeah, there it is there. And then this is log of n. Yep. This one's cool. How would I have thought of that one? Like, how would that have come into my head? So I'm just gonna look at it once more because I just think it's kind of cool and just try to think about it a little bit more. Okay, so I have MP. So I am given a sorted array, so I have information on I have information on kind of the placement and where that will be in relationship to the other number, okay? And I also, it's A plus B equals C, and I know A because I'm currently at A, and I know C because that's the target, and now I just need to find B. And so I can locate B by storing everything that I've already seen in a map, where the map, the key, is the value that I need, or the key is what I need, the number that I need. The value is the index at which I will return. So I'm kind of saving that index value along for the ride. Okay, cool. Awesome. So there we go. We got this problem too. Look, we're just keep knocking the problems out. So next video is going to be the next Leetcode video. So if you want to watch that video, subscribe. That would be awesome. I would love to have you around. And yeah, thank you for watching this video. My name is Timothy Lee Grant, and I'll see you guys in the next video. So goodbye.